Hello everyone and welcome again. So let's start off yet again with another one of these sorts of problems to begin with. So you can see I've marked some arcs for you. This is 110, this is 20, and our goal now is to get this angle on the outside. So I'd like you to again try this out, pause it, and give it some thought and give it a go before you continue the video here. Alright, so remember like before, right, if you recall, we were missing a critical piece of a critical line here, right, because that allowed us to create triangles and exterior angles. So I wonder if we can do the same thing again. Well, I mean, just like before, we want to connect 2 points that haven't already been connected here. The center's not going to help us out too much, but we can kind of do the same thing here. So you're going to see that connecting either BD or AC is going to be the solution here, and it doesn't really matter which segment you connect, you're going to end up with the same thing here anyway. So we connect AC here. Again, we create two inscribed angles here. ACD is an inscribed angle, so that's a 10-degree angle here. BAC here is an inscribed angle, so it's 1/2 of 110, so 55 here as well. So now we know that PAC here, this angle like this here, is 180 minus 55 because it lies on a straight line, which is 125 here. And as a result, now I got two angles of a triangle, 125, 10, and P. So now I know that the measure of angle P here, right? We can go ahead and write this here. The measure of angle P here is going to be 180 minus 125 plus 10. So it's 180 minus 135 here, and that yields us a 45-degree angle. You know, alternately, you could have also noted that this 55 here is an exterior angle, so it's going to be equal to the sum of 10 and the mystery angle here. And now we know, okay, we got a 45 here, so we note that this is actually similar to that of what happened last time, right? Last time we saw that with two chords that intersect inside of a circle, the sum of the measure of that angle formed between them was 1/2 the sum of the intercepted arcs. But now, if you look at this, that's not the case anymore. We have a 110 and a 20. Now, instead of adding them, it seems like we're subtracting them and taking half the difference. So what we have here, ladies and gentlemen, is something that looks like this. So the measure of an angle formed by the two lines intersecting outside of a circle is 1/2 of the difference of the measures of the intercepted arcs. And again, we can kind of do this in exactly the same way here. So you'll note that for something like this here, right, we can kind of do exactly the same thing we did before. So in this case here, right, here's AD, here's BC here, and here's P on the outside. I want to show, right, here that measure of angle P is 1/2 of BC minus AD, right? So we can do exactly the same as what came before. We drew in AC here, right? We can do it again. Now, you know, you can do it again. I'll draw in BD just to be a little different this time. But you'll notice that it functions in exactly the same manner here. We notice that the measure of angle BDC here, right, is 1/2 the measure of arc BC here because, this is an inscribed angle. So that's going to be important here. We can mention that. Furthermore, we have another inscribed angle here. So we have this angle here. We also have this angle on top. We know the measure of angle ABD here is 1/2 the measure of the arc it intercepts. So that's AD here, which is also inscribed as well. And now, if we look at triangle PVD here, we have an exterior angle, right? So we can write that the measure of angle BDC equals the measure of angle ABD plus the measure of angle P. So this is an exterior angle here, right? We know that that's an exterior angle in that situation here, so we can kind of put it all together. And now we can just substitute in what we need. So BDC here, so that's 1/2 the measure of angle of arc BC equals the measure 1/2 the measure of arc AD here plus the measure of angle P. And now we can just subtract from both sides and get the measure of angle P is 1/2 the measure of arc BC here minus 1/2 the measure of arc AD. So we can do a little bit of factorization here, got to set it up, and get 1/2 the difference of the arcs here. Right? So we can see it's 1/2 the difference of the intercepted arcs. Now note here one important thing about this particular theorem here is that note it mentions two lines here. It doesn't tell you exactly what the lines are. So remember that we have multiple types of lines that are created with circles here. You have tangents, you have secants here. And you'll note that every single one of them functions in basically the same way here. So for one case here, right, we can have two secants, right? So our two secant case here will look something like this here. And we have just this here, and this is just the plain old secant that we had here before, right? Here's BC, here's AD, here's P, and we see that in this situation here, the measure of angle P equals 1/2 of, so note that we can see the two arcs that are intercepted. Here's BC, and here's AD here. These are your two intercepted arcs. So it's 1/2 of arc BC minus arc AD. Okay. Now, of course, this is not the only case that exists here, right? We can actually do other cases as well. We can have in this situation, right? And we can have one tangent, one secant, right? So that would be, again, we draw the circle here. This time we have a tangent like so and a secant like this. So we note that in doing this here, the number of intersection points with the circle has actually decreased by 1. So you have A, B, A, D, and C here. So in this case, angle P on the outside, but notice now that it's still going to be 1/2 the difference, but the difference is going to be slightly different here, right? The difference is now AC, so you can see that this arc is now here, minus this arc here. You can see that this arc exists here. Right? And now you can see that now the two intercepted arcs, they both share a single point here. And then finally, there's one final case here, and that's two tangents. And you'll see that the two tangents case works out very similarly as well, right? We can kind of do this here. This is our setup. We have something like this and something like this here. And now there are only two intersection points here, A and B. So now our two arcs, as you can see, actually join forces here, and they actually create the entire circle. But remember, we're not finding their sum, we're finding their difference here. So we can kind of see this is our case here like so. And now in this situation here, the measure of angle P, like this, is yet again half the difference. But this time the difference is going to be a little bit different here, right? So we have to use the big blue one here. So here's C. We can say the measure of arc ACB minus AB here. So you'll note that even though we have three separate cases here, three separate situations for us to really worry about here, all of them still function in pretty much exactly the same fashion here. It's 1/2 the big arc minus the small arc here. And you'll end up with a positive value here. All of these should end up exactly the same thing at the end. All these will deal with angles that are outside of the circle here.